In the last videos, we were looking at graphical illustrations of the forwards and backwards algorithms. In this video, we'd like to have a look at some of the comparisons of the complexity and the calculations required in the backwards and the forwards algorithm. So the problem as a whole, if we only had 3 decisions to make for each of the 10 increments, would give us about 59,000 different valid schedules. The backwards dynamic program enabled us to only do 30 calculations and come up with the best cut-off grade policy. Now, each iteration of this forwards algorithm also takes 30 calculations. And if we were to do 10 of these iterations, we would also guarantee that we had the best solution. So you can see if you didn't have time varying properties and you didn't have multiple resources and pushbacks, or if you had stockpiles, the most efficient algorithm, this backwards dynamic programming algorithm, could be used to only use 30 calculations and get to the best solution. With these extra complexities, that has increased to 300 different schedules that we've evaluated, but still this is quite a lot lower than the 59,000 total combinations. So let's look at the problem size and the number of calculations that we do for a more realistic problem. So say we have 62 different cut-off grade decisions that we're making for 10 different increments of material. We'd end up with 62 to the 10, or approximately 10 to the 18 different combinations of valid schedules. So the backwards algorithm would only require 620 calculations to get us to the best schedule. Each iteration of the forwards algorithm would require 620 calculations. And if we were to do 10 different iterations, we would end up doing 6,200 calculations. Now, although this seems like a lot of calculations, it's actually way less than the total number of valid schedules that are possible. So we've saved a huge amount of time. And this algorithm, even though the forwards method is slightly more time consuming than the backwards algorithm, because it handles time varying properties in a better way, and because the forwards algorithm handles time varying properties and multiple sequences and stockpiles in a better way than the backwards algorithm does, the forwards algorithm is still a very efficient method to solve this problem. So because it's so efficient, what we can do is we can throw more at the problem. So instead of just looking at cut-off grade, we can also look at the throughput recovery relationship, or the sequencing, or the throughput recovery and the sequencing and the cut-off grade all at the same time. We can start to throw more at the problem and solve more policies simultaneously. So this is what's used in COMET 1 and in the COMET optimal scheduler. Now, Ken Lane makes a very interesting observation about this formulation. He says that the maximization is no more difficult than the maximization of C itself. So what this allows us to do is to throw more at this problem. If we can not just optimize the cut-off grade, but we can also optimize the throughput recovery relationship, or the sequencing relationship, or how much to put on a stockpile and take off a stockpile, or all of these things combined together in one optimization. This is what makes this algorithm such a powerful algorithm and so useful for strategic planning. I hope you've learned something from this video on the forwards algorithm used to optimize cut-off grade and some of these other operating policies for a mining site. I'll look forward to your comments and feedback. In the next video, we'll be going through the derivation of the formula used in Ken Lane's book, so you'll be able to understand how to calculate the opportunity cost, which is discussed in that book.